Hello everyone, welcome to our special episode of Conversations about the Cosmos. We have no time to waste because we are here at the Starmus Festival. My name is Samuel Kovacic, as usual, Norby Werner. We have special guest Joel Parker. Welcome.
Thank you.
So, Norby, you have a special question prepared. Shoot.
Special question. Yeah, we are at the Starmus Festival, and you are an astrophysicist who also does acting, and you are a drummer, and you have your own radio show. So, I mean, you are a person who is combining art and science. Can you tell us your perspective? How is art and science similar, or how do they complement each other in your life? At least your own perspective.
Sure. Well, in the grander scheme of things, art and science are both ways to explore. And sometimes they can explore some of the same questions of, why or human experience. And they can just take different approaches. There is this stereotype of, the scientist in the lab coat who...
You can point the finger.
But that's a very nice lab coat.
A little bit too formal.
Yes. Who only just, knows the science, knows equations, kind of the nerd, and, doesn't do anything else. And the reality is when you meet a lot of scientists, you find that they have some very interesting artistic sides to them. They paint, they play music, many, many different sides that are creative in a way that a lot of people, don't think of stereotype for science. But they are both creative approaches. People can think of what creative is for an artist, of coming up with images or ideas or words or stories. But scientists have to be creative too. It's a great job. You get to think of questions that haven't been answered yet. So that's one aspect of the creative part, is what do we not know? And then the next creative part is, how do you get the answer? How do you do the approach to answer that question that hasn't been answered yet? So, I think those are some of just the general similarities. For myself, I find that they are a nice balance of each other. When I maybe get tired of doing the science or coding or something like that, being able to do a show, do my radio show or acting or bang on the drums or something like that, is a nice break. And also, if you're thinking hard all the time, sometimes you can get stuck. And doing something else can kind of loosen up your thoughts a little bit and maybe come up with ideas you hadn't thought before. So I really think they're both similar and very complementary.
But you said that not only art, but also science is sometimes creative. But isn't it that science needs to be creative to come up with something new? And with art, sometimes you just repeat what someone else... We just saw the Philharmonic Orchestra, and they have to repeat and learn it pretty perfectly, but they keep repeating it. So isn't actually science more creative? Because by repeating the same calculation over and over and over, I wouldn't learn anything new.
That's true. Of course, when you go to college, in grad school, you're doing the equations over and over and over again. That's like the performer's rehearsals, that you get that intrinsic understanding of what the equations are telling you. Just like an artist, a musician, gets the fingering so they don't have to think about it. And that then can loosen up the creativity. Sure, symphonies, some artists will do the same thing over and over. But there's always some little variation. Unless you're a studio musician, you're always doing everything exactly the same. But, a lot of them like improv too. And improvisational music, you're just making it up on the spot, and sometimes it works, sometimes it doesn't. Just like in science, you have an idea. Sometimes it works, sometimes it doesn't. So, and to play devil's advocate, some people in science, they kind of do the same thing over and over, just maybe slightly different. They've done this paper on this topic, and they'll do a next paper that's pretty much the same, but maybe slightly different. So we're all human, and we all have different abilities to be creative, to be improvisational, or feel in our comfort zone of kind of doing similar things.
And maybe there is, I'll let you ask a question, but there is a similarity maybe because you just mentioned that science usually evolves very slowly by small steps, and so does art, music, and so on. But then comes Einstein, and then comes, I don't know, David Bowie or someone who may...
Right.
Someone who is at first misunderstood, not appreciated correctly, and then we ordinary humans get to understand. So maybe there is another similarity, gradual evolution, and then just
that's right.
Huge jump.
No, I think in both science and the arts, there are these moments of where someone just has some very profound insight or new idea or new way of looking at something. You know, Einstein just talking about, light, traveling along with a photon, clocks and things like that. Different ways of looking at something that others maybe hadn't before. And yeah, exactly. Same with artists, just whether they're a musician and there's a new sound or concept, or visual artists with different ways of putting together visual experiences. And then everyone catches on and go, that's a great idea. And then they expand, and then there's slow evolution. So that's a very good point, that both of them are, evolution punctuated by these moments of some significant change. I like that.
Yeah, I often wonder, because I know so many people around me who are scientists, who are also musicians. How is it compared to the regular population, the other population, whether it is more often or not? And I don't know.
I don't know either. And someone must have done a study about that. If not, you just came up with a great idea to do a study.
Yeah, somebody should do the statistics.
Someone should do that. At many science conferences, you'll hear a lot of people say, like, this is all great, but someone needs to do this, and someone needs to do that. And sometimes someone will eventually end up doing that. Maybe just from the background as a scientist, I always try to think that, the Earth is not in a special place in the universe, and we are not special as humans, right? We have the same interests and the same behaviors as anyone else. So I guess my assumption, my hypothesis would be that it's pretty similar. But there may be something about how the brain works, where working through, having a brain that's wired in such a way that you can work well with the logical progression of development of a theory, and something that's similar to someone who can do a logical development of writing a story, or the logical development of learning the pattern of music. So there may be some overlap and reason why the two feed off each other. So yeah, maybe.
So to slightly pivot towards space, you probably know of the Voyager plates and the content carried by Voyager probes. Are you happy with the artistic choices made by the Voyager team?
So you're talking about how those images and the music, everything.
Would they miss something important? Would they add to the collection?
They can't avoid but miss something important. There was, for the music, I think one of the songs was like Johnny B. Good or something like that. Yes. I also just read an article where, I don't know if you know Sun Ra, musician. He actually sent an application to NASA, suggesting his music. It wasn't selected. By making choices, you're automatically making choices against other things. And even if you have a committee is going to have a certain bias about what is picked. So I'm sure they tried their best, and they had images and sounds of nature and things like that that they thought were representative. But I'm sure there were a lot of people who would argue a lot was missed. Maybe some of my favorite music would have been picked otherwise, but yeah, it's difficult to make the choices. A lot of science, a lot of art is not necessarily what you choose, but what you don't choose.
You were involved with the New Horizon mission, which is also leaving our solar system. Wasn't there a discussion in the team to also include a golden record?
So there was some discussion about that. Of course, when you have a space mission, mass is money, and you don't want to add a lot of things onto it. So there were a few small things, but there wasn't anything like a golden record or any message.
Maybe aluminium record would be.
Yeah, right. No message to aliens or anything like that, other than if they happen to run across the probe, that's in itself a message. We have talked about uploading in software to the spacecraft some type of message. Of course, over thousands of years, the memory will degrade, and that message will be sketchy, if not, unreadable. But there have been some suggestions for that, because New Horizons is zipping out there. It's going to be going past basically the heliosphere, the influence of the sun, out into the rest of the galaxy, the interstellar medium and beyond. So there has been discussion about that. As a counterpart to that, so another mission I work on is called Lucy, which is visiting the asteroids, the Trojan asteroids that are in the same orbit as Jupiter. And this spacecraft will never leave the solar system.
Unless you made a mistake in calculation somewhere.
We made a very large mistake, but so far, so good. And that's in an orbit that basically will be a stable orbit between the Earth and Jupiter for the most part. Those distances from the sun could be for millions of years. So what we did is we did put a plaque on the Lucy spacecraft. And that plaque has a little diagram of the solar system showing, Lucy's trajectory. And it also has a number of quotes picked from writers and from around the world in some different languages, but still very selective. But, it has Carl Sagan, because it's the Lucy mission, which has a little connection to Lucy in the Sky. We have quotes from all the Beatles, and other artists, musicians. Brian May is on that as well. But the thing about this plaque is, since we are not leaving the solar system, we view this plaque as a message to our descendants, those people from Earth hundreds of years from now who may decide to go pluck the spacecraft out of its orbit and put it in a museum somewhere.
Do you think this really will be done by a future billionaire, too bored on Earth, just catching up?
I cannot predict the behavior of bored billionaires. And this is exactly, you may want to go down and view the Titanic. You may want to go and grab Lucy, So,
or even the Voyager.
or Voyager, that'll be a bit of a sprint, but it's still possible. So yeah, it's a message to ourselves. And I liked that idea.
we talked, what was it, 2-3 days ago during the lunch, and I told you, I say, great seminar about the Lucy mission, and I have terrible face memory because the seminar was done by you in Bratislava. When you said that there are some surprises along the ride, like you found new asteroids you didn't expect, and it's probably very hasty mission suddenly turning and trying to capture. So can you describe these sudden surprises?
So when you design a mission, you have everything planned out well ahead of time. In fact, you have a pretty good plan when you propose the mission, of course. You want to say, these are the things we're going to do, and this is why we are asking for these, tens, hundreds, millions of dollars to do this mission. So you have it pretty well planned out. But science teams are creative, and they come up with ideas all the time. So the first idea you have will likely survive, but new things will be added on to it. With the Lucy mission, so we launched in October of 2021. And after we launched, we were looking at the flight path, and one of the fellows involved with the mission noticed that we would be passing close, just by chance, to an asteroid. Now, close means about 65,000 kilometers, but that's close in space. And it would take very little fuel for us just to do a little change to go do a flyby of this asteroid.
What does it mean, a little fuel? Because I'm a theoretical physicist. I get to ask knife questions. So what is a little fuel? It's like this or?
Little fuel could be on the order of grams to kilograms, but not many kilograms. But enough, if you change an orbit early on, that can make a big change later. So the sooner you want to make a change, you can use less fuel to make that adjustment. It's kind of like the lever arm. So there was this asteroid we were going to go by, and we decided to use it as basically a rehearsal. Because we were confident the spacecraft would work, but it's just like a musician.
Yes.
You want to do a rehearsal, make sure you work out all the technical difficulties, all the chords are plugged in before you, start playing those power chords. Same with a spacecraft. You want to make sure all the instruments work together well, that the data path from the instruments to the spacecraft to the ground, end to end, all works. And for the Lucy mission, we also have this system called the Terminal Tracking Camera, but it's basically to autonomously point the spacecraft as it gets closer to a target. And that saves us a lot of planning, because the spacecraft will know exactly where the target is. And we don't have to guess, well, it's going to be kind of maybe over here, or kind of maybe over here.
It knows the humans are interested in this point.
It knows, right.
Using fuel or gyroscopics?
So, we have gyros, and we have a pointing platform, so it will use those. And this allows us to plan for how it's going to point and things like that. So this was our rehearsal to do that.
The camera is pointing independently, or you have to point with the whole spacecraft?
So you can do either, but the spacecraft is on its path, and unless you use fuel to change that path, it's just going to follow what it does. But the attitude of the spacecraft can be controlled by the gyros. And also, all the cameras are on this platform, so they all point together. And so you can adjust the pointing of that platform as well. It's actually, you can have the spacecraft point so that it stays pointing at the targets or that platform.
But the point is that you need to point with the spacecraft because the camera cannot point anywhere, only certain angles.
That's exactly right.
And then with your high gain antenna, you will not point at the Earth, so you will not be in contact with the spacecraft.
Right. Yep. So there are all these different constraints. That pointing platform has a certain range that it can point. So the spacecraft needs to be positioned so that you have enough freedom to do that. During the encounter, we're going to be all focused on the target that we want to observe, the asteroid. So we will be slewing the spacecraft so the antenna will not be pointing at Earth while we do the flyby, because we're all interested in that. So the spacecraft is going to be doing all its work, doing it autonomously, and when it's done, it's going to point back to the Earth and then send back all the data. So this flyby of this asteroid that we did not plan for was a rehearsal of all of that, and it worked beautifully. And it made all the engineers very happy. It made all the science team very happy that, you know, everything went really well. And everyone knew it would go well, but they were still surprised that it went as well as it went. So, you know, it reduces risk, which is the whole point of a space mission, other than getting the science, is reducing risk, minimizing any possible problems so that you can get the science you want to get.
And yesterday you told us that there were some unexpected discoveries with this asteroid. So
we went by this asteroid and we thought it was an asteroid that wasn't well known, wasn't of much interest. It didn't even have a name. So we gave it a name. We through the International Astronomical Union, we were officially able to give it a name, Dinkinesh, which is an Ethiopian name for Lucy, the Lucy fossil, paying homage to that fossil that the mission is also named after. And we just thought it would be a plain chunk of rock asteroid, but it's good practice. When we flew by and we got the images looked very strange. We saw the asteroid, but there was this, it looked like a bump off the edge of the asteroid that we didn't expect. Then when we got a few more images and looked at them, we realized that bump moved, and it was actually a moon, a satellite of this asteroid that we didn't know about. So that was one surprise. And then when we got to, after we flew by and looked back and got a better side view of the moon, we saw that that moon was actually two pieces stuck together. What we call a binary asteroid. So we had never seen a moon of an asteroid that was itself a binary. And so now the theorists have to go back and figure out how do you form a binary asteroid where the moon is a binary, and everyone has fun.
You know, the funniest thing is that 2 days ago we were doing an interview with Frank Marchis, who discovered the first triple asteroid.
Right.
And basically this is an almost triple where...
It's an almost triple, and that's the question is, how did it form? Was it in fact a triple? Could that original asteroid have been hit by something that threw out a bunch of debris, and that debris eventually turned into a moon that was a little binary system that eventually touched and became a stuck-together asteroid? Or did they form from two different impacts? That seems maybe less likely. So a lot of it is now the theorists trying to figure out different ways to form it and what is the most statistically likely scenario.
So we mentioned here two missions, New Horizons and Lucy. And both of these missions have, the ultimate scientific goal of both of these missions is to learn about the formation of our solar system through studying the pristine material.
Right. Yep. It's, these are the fundamental questions that the scientists ask, and it goes back to to what artists do as well. And the questions a 2-year-old will ask, why?
Yeah.
Why?
Questions of origin.
Why does that? Why does that? Where did I come from? And, it is the question of origins that I think we all want to know where we came from, how we got here, and what more is there.
So again, I'm a theoretical physicist, so there was a big cloud and it collapsed and ta-da.
Yes.
So how can...
That was pretty much it.
Yeah, long story short. But how can asteroids help us to clarify some of the details?
So you can think of asteroids and comets. So I was also on the European Space Agency Rosetta mission. Same idea of question of origins. And that target also was a contact binary. Yeah. So we think that things like asteroids, comets, these small bodies in the solar system, they're the leftover debris from that cloud of gas and dust that kind of collapsed. It created a disk, kind of like a pancake around the sun. And parts of that disk formed planets. Mm-hmm. And then all the rest was just the leftover debris, the leftover small bits that couldn't form into a planet. Planets, like studying Earth now cannot easily tell you anything about what Earth was like 4.5 billion years ago, because there's all this processing going on with, convection in the mantle and the continents, subduction and everything like that, and chemical changes with the atmosphere and the ocean and everything. So there's not, you can't study pristine material that the solar system formed out of by studying planets, because they've very often been very processed in some way, physically, chemically, what have you. But the small things, those little chunks of ice or rock, probably are less processed. And the further away they are from the sun, the less processed they get. If you're really close to the sun heats things up like baking in an oven. You'll lose all your water, things like that. So you'll lose some of the, the chemical ratios and things like that. That might have been the case 4.5 billion years ago. But as you go further out and look at these small bodies in the solar system, especially the icy ones that have been cold for maybe all of their lifetime, they might still have the chemical signatures or the physical signatures of how the solar system formed. The ratio of, ice to silicates and things like that. Or if you can understand the physical property of an asteroid, is it a solid chunk of rock? Or is it what we call a rubble pile, where it is lots of small little bits of rock that are just lightly stuck together by gravity? There are different models about the formation of the solar system that say that they're more likely this, or they're more likely that, or that they formed as binaries. So as we visit these and can understand what they're made of, how they're made, and their dynamical and physical properties, then we can start saying these fit that theory more than that theory. And that can narrow us in on what is the most likely scenario 4.5 billion years ago.
So, as I told you yesterday, during my bachelor and master thesis, I studied asteroids and comets, and I still love the topic. So whenever I'm reading the archive, I like to read the abstracts of some of the papers on this topic. And a couple of months ago, I read about the Trojans, and the abstract said that some of the Trojans might be there since the beginning of the solar system, that it's so stable that actually those Trojan asteroids might be just as good to study the origin of the solar system as the trans-Neptunian objects in the Kuiper belt.
Exactly.
And I was really surprised, and
Yeah, no, so thanks for bringing that up, because that was the whole point of the Lucy mission. So the reason we're going to these Trojan asteroids, which they're in the same orbit as Jupiter, but they are leading and trailing Jupiter's orbit. And these are very stable positions called Lagrange points that objects can stay in for literally billions of years. So things that were captured into these orbits, these Lagrange points, will stay there. And if they were captured there 4 billion years ago, chances are they're still there. They can be a little leaky, but for the most part, they're there. One of the models of the solar system we have is that the solar system formed a little more compact than we see it today. And then there was this migration of the outer planets, Jupiter, Saturn, Uranus, Neptune, that migrated out. And as they did that, they scattered all these small bodies, all the debris that was left over, the asteroids and the comets, scattered them all over the place, but some of them got trapped in these orbits around Jupiter. And we think that this migration happened very early in the formation of the solar system. So the objects that were trapped there probably got trapped there 4 billion years ago and have been in this storage cabinet, this freezer, ever since. And we think that, in addition, that those objects that got trapped there may have come from many different distances from the sun. So by going to this one area where the Trojans are, we're actually, we think, able to sample objects that formed at a range of distances in that original disk of the solar system by just going to one place, the Trojans.
But will you be able to determine at what distance it formed, or you will just see?
So that's the question. We know that these Trojans already have diversity in what their spectra look like, their color, whether they're binaries or not, whether they're fast or slow rotators, whether we think they're part of what's called a collisional family or not. So there is a lot of diversity. And the question is that diversity primordial? Is that an indicator of where these objects formed? You know, did the redder objects form further out in the solar system? So we're hoping that when we do these flybys, and we're not going in orbit around these are flybys. We're hoping that when we look at things like what the surface looks like, with spectra, we will be able to look at the chemical properties of the surface. We'll be able to get how the temperature responds, what the thermal inertia is, so we can understand a little more about the interior property and whether it's a rubble pile or something more solid. And all these different lines of evidence have different pointers to a different formation theory and a different origin. So we're hoping that all of these together will be able to solve that.
So what is the most interesting questions that you would like to find an answer with the Lucy mission?
Oh, there's so many. The great thing about these missions is you go out to answer these questions you have, but you have all these beautiful instruments on your spacecraft that will end up sending you data you don't expect, as well as the data you do expect. And so the thing I always look forward to is getting data, getting information that I didn't expect.
Yeah.
Because, you know, getting the answers you want is good too. But so understanding the diversity, I think, is really important. And that can really tell us a lot about the origin of the solar system. But yeah, I'd have to say finding out what we don't expect, the surprises, are what I'm looking forward to.
So to let your imagination run wild, imagine in 10 years we buy New York Times, cover page is your face. Great discovery made by Lucy mission. So what is the article about?
So let's see, getting the front page about Jupiter Trojan asteroids.
You have to, yes.
You really have to stretch.
Running wild.
I guess a picture of a spacecraft on the asteroid would probably be that.
You found a parking lot
But
there.
don't quote me on that, although I know it's now going to be on the internet forever. Realistically, the things that I think would be the likely surprises are, first of all, finding out things about the shapes of these objects, and also, the moons they have, because that can answer a lot. The being able to say something very profound about the formation of the solar system, when the planets formed, when the disk formed, when this disruption of the migration formed, will be very interesting. Understanding, finding if there are hydrated materials, if there's water, on these objects. We expect ices, what kind of ices, organic compounds and molecules. So not life, we're not going to find life, but do we find the building blocks of life on these things? The amazing thing about life is every time we keep looking, we keep finding the building blocks, all the pieces you need to make life as we know it. So this is, leading us to believe that it's like all the elements are there. You have a kitchen with all the ingredients of a cake. So a cake can be made. The question is, do the ingredients get put together a lot to make a cake often? Or hardly ever? So the more places we go to find organic molecules, the more it makes it likely that there is life elsewhere. And that, of course, that is not one of the Lucy missions, is to find evidence for life. But it would be another important piece to which I think that is ultimately the fundamental question that I think a lot of people ask is, are we alone? Is there life elsewhere? And, right now the answer is we are alone because we haven't seen any evidence of life out there. And we're either alone because there is no life out there, or we're alone because they don't want to talk to us.
I would completely understand that.
Yeah. Could be many reasons. So that would be kind of the next, another piece of evidence. The real front page of the New York Times someday would be if we have absolute evidence of life elsewhere, whether it's microbes on Mars or Europa or somewhere else.
But you said it won't be Lucy.
It probably will not be Lucy, but if it is, I guarantee it'll be front page.
But you were on the New Horizon team, which made it to the New York Times front page.
We did.
There was the heart on Pluto.
The heart
right?
of Pluto.
So what is your favorite discovery of the New Horizon?
Oh, that Pluto is, there's always this discussion, is Pluto a planet? And it's like Pluto. My first answer is always Pluto is what it is, regardless of what we call it. It's a Kuiper Belt object. It's a planet. I think of it as having dual citizenship.
Yeah,
You're trying to avoid the responsibility of choosing.
Yeah.
Is it or isn't it a planet?
There are good reasons. It all depends how you want to define a planet. And definitions are important because they help us categorize things. But the scientific interest of Pluto will be what it is, regardless of what we call it.
That's just the name.
But it's just a name. So I still I still call it a planet because I grew up calling it a planet. But the thing that really struck me about Pluto is whether you call it a planet or not, it is a world. It has an atmosphere. It has active glaciers. So this is, people thought Pluto was just going to be this frozen ball of ice out at the edge of the solar system. And it has glaciers. Now they're nitrogen glaciers on a water ice bedrock. So instead of on Earth where you have water ice glaciers on a solid granite bedrock, you now have nitrogen glaciers on a ice bedrock. So the physics is completely different on how the glaciers move and flow, but they're active. And this is a planet that should be cold and dead, and we still see active glaciers. So there has to be enough heat source for active glacier overturning convection and things like that. So that, to me, was the huge surprise to Pluto. Was it is incredibly diverse. It has these old pitted terrains of mountains. It has, ice fields with these strange pits in it. It has these beautiful glaciers that have no pits and no craters, meaning they're extremely young. We use craters on objects to tell how old they are, because the longer you're sitting out there, the more you get hit by things. So how many craters you have, tell us a little bit about how old an object is.
And now I will jump because while you were talking about Trojans, I was just thinking about craters.
Yes.
Do you expect many craters on Trojans or little? Because the cratering in the inner solar system came from the Great Bombardment. When Jupiter launched many bodies to the inner solar system. But these Trojans, if they were orbiting there together with Jupiter, then they couldn't be hit. So
yes, we do expect craters. But what you call the late heavy bombardment, this was a result of, this planetary migration I mentioned, where the big bully of the solar system, Jupiter, and then Saturn, Uranus, and Neptune migrated out. They scattered all these small things outward, but also inward. So the Earth and all the inner planets got pummeled by all these objects. We can see that on the Moon because it has a very good crater record. The Earth gets processed a lot, and it's harder to see the craters. So even during that bombardment period, there was a lot going on. You can just think of billiard balls just scattering all over the solar system. So things got hit a lot. So there will be some from that, but also there's still a lot of material out beyond Jupiter in the Kuiper Belt that eventually gets disturbed, it gets turned into comets or what have you, that still comes in. And it still will hit things like the Jupiter Trojans. So we do expect craters, and we do expect the craters to be able to tell us about the ages, and then the different sizes, the size distribution of the craters will tell us something about the size distribution of all that extra debris out beyond Neptune. So the craters will tell us a lot.
So the New Horizon is continuing beyond Pluto, and it visited some Kuiper Belt objects.
Yes. So
what did it find?
So our prime mission was to explore Pluto and the Kuiper Belt. So, Pluto I call the king of the Kuiper Belt. So it was the first Kuiper Belt object discovered, largest one in the Kuiper Belt. And we knew the existence of the rest of the Kuiper Belt really starting in 1992 when we started discovering these other Kuiper Belt objects. Right around the time we started finding exoplanets around other stars. It's been kind of a race, finding more Kuiper Belt objects and more planets around other stars. It's been amazing growth in these areas of astronomy. And so after going by Pluto, we went another billion miles. and went to visit a Kuiper Belt object that we hadn't discovered yet when we launched, it's now called Arrokoth. And we flew by that a little time later on New Year's Eve 2019. And that was also another surprise. It itself is also a contact binary. So this is telling us something. Binaries are common.
They seem to be very common, yeah.
Binaries are common. Contact binaries are common. This is telling something about a common process in the formation of the outer solar system. And so Arrokoth, itself was very interesting. The two bodies were actually kind of flat. So they weren't round, like round rocks sticking together. They were more like kind of hamburgers sticking together on edge a little bit. So that was very exciting. And we did crater counts and, things like not very many craters on that. So that was something that was very exciting and unusual. And we are now looking for one more target that we can, we're following a path. The spacecraft is on its way. It's going where it's going. We have very little fuel to be able to change the course of that path at all. So we are looking for any objects that are along our flight path. So we're pulling out all the stops using the biggest telescopes on the ground, in space, to look along that flight path to see if we can find any more targets for New Horizons to fly by. So right now we're doing our best to conserve fuel. We're not doing a lot of other science. We can do amazing astrophysics with New Horizons because it's so far out in the solar system. It's away from all the gas and dust inside the solar system. So we can look at the ultraviolet sky out beyond the dust of the inner solar system. There's a lot of heliophysics, study of the sun and its environment, and astrophysics. But right now, we're conserving our fuel, crossing our fingers, and doing our best to find one more target to fly by. So that's what we're focusing on right now.
And in our conversation, this terrible word, in our discussion, we are moving toward the edge of our solar system. Do you expect there might be a planet looming there?
So there have been a lot of theories about, Planet X, what have you, out there, pretty much in the Kuiper Belt or elsewhere, something large. So we're talking, bigger than Pluto, maybe Mars size. Some people have thought larger. There's some curious aspects of the orbits of these distant Kuiper belts that might indicate there is some other object out there. It's a very subtle hint, and some people argue it's just a bias in where we look to discover these objects. And other people say they're doing observations that they're doing their best to do it in an unbiased way. So any strange distribution must be due to some other planet. So this is a discussion that's going kind of back and forth right now.
And what is your estimate? If you had to bet money, it's on one more planet, or this is it?
So I'll do my head and my heart. In my head, I think it is unlikely. A lot of the ideas that come up aren't definitive, and there's a lot of good arguments against them, but there's still unanswered things that could mean there's one out there. So just thinking, I think like chances are no. From my heart, I would love there to be yet a new discovery.
I think we all do.
And just the history the history of science, we're constantly being surprised. And when we think we know everything, there's a scientific revolution, whether it's quantum mechanics or
slow evolution.
Relativity.
Yeah.
You have from slow evolution to revolution.
Yeah.
And, you know, this wouldn't be a huge, you know, turnover of everything we've ever known about planetary science, but it would be a significant discovery that I think would be very exciting. That's probably a discovery that's going to be done with ground-based telescopes, because we can just have much bigger telescopes or arrays of telescopes that can cover a much larger area of the sky and go much deeper. So if that discovery is going to happen, the spacecraft are great. Telescopes in space are great. They can do things we can't do from the ground, but it still all comes back to that kind of that stereotype, that tradition that people think of when they think of astronomers, of someone working on a telescope on a remote mountain in, you know, on Hawaii or in Chile or Canary Islands or somewhere, just looking up at the sky with a big piece of glass. And one night, they'll see this little dot that's moving among the stars. They'll do the calculations. They'll find out that it's a planet out there further than we ever saw. So
fingers crossed.
That's what I hope for.
I think it's nearly lunchtime, so we maybe have time for one or two questions. Do you have a question in mind?
No, I think this was a really nice point.
I'll just come for a little gift for you. Because we are terrible at marketing, but we made new book. It's Conversations about the Cosmos. Next one we will call Discussions about the Cosmos. And this combines art with science. So
beautiful.
We'll send it to them.
Oh, thank you very much. The combination, you know, I really think the combination of art and science is essential.
Unfortunately, it is in Slovak, but you can look at the pictures. These are universal.
How else do you think I'm going to learn Slovak, right? So, no, and that's true. Pictures are universal. And that's another reason why the arts are important, is they can bridge, and people who do not share a common verbal language, you can still share a common visual language or experiential language. So being able to communicate multimodal in different ways, I think, is important.
Maybe there is one more point. You mentioned that you are planning missions years ahead, and then you have to think very carefully about small nudges that can change the result completely, which is maybe a good advice to young people. You can plan your life ahead, but small nudge here and there will change the result completely. So maybe do you have a message for our young listeners and viewers?
I absolutely do. So for all the early career scientists, all the young people who think science can be a career, you can do that for a living. You know, I guess what I usually say is, you can plan as much as you want, and maybe that plan will come out exactly like you want it. But all of the scientists I talk to, it is the little unexpected moments that change your path greatly. It's like that little bit of fuel that you use now that changed the course of your spacecraft 10 years from now. It could be a teacher that you meet that you suddenly go, oh, wow, I want to do what they're doing. It could be just going to a planetarium or a thing like Starmus. I thought I would go into a completely different type of physics. And then it was the mentors that I met, the teachers and the researchers who I respected. And I thought I would like to do what they're doing. and they took me off in a different direction. And I learned how to do observational astronomy, looking at stars. And then I found out some colleagues looked at planets. I go, okay, I could look at planets. It was a completely random walk. So as much as you may plan something out, leave yourself open for what might be unplanned. Leave yourself open and for an opportunity, and don't be shy about taking advantage of it. You can actually walk up to a Nobel Prize winner and say hello and shake their hand and ask them what they're doing. And they may actually tell you something that will change the direction of your life. So, make plans, but be ready for opportunity. That's the best I could say.
Probably best anyone can say. So thank you for coming.
Sure, thank you very much. I really enjoyed this. Thank you.
So this is the end. You can find us online, all of this by this time. So thank you again and see you next time.
Bye-bye.
Thank you. Environmental makes it more.
Romča, Luka. Ty to vyslavně, co mám to pak dát na tom? Jo, tam nebude ta, co tam zatím celou dobu.
From the acting background, I just get louder to compensate. So hopefully I didn't get too loud for the sound.